Welcome to the Math Ed Podcast. My name is Sam Otten from the University of Missouri, and joining me is Melania Bernabeu, who's from the Universidad de Alicante, which is in southeast Spain. So, Melania, thanks so much for being here.
Oh, thank you for inviting me.
And we're going to be talking about Melania's article that was published recently in Educational Studies in Mathematics. And the article is entitled Primary School Students' Understanding of Polygons and the Relationships Between Polygons. So, Melania, I have some young children myself who are in elementary school, and so I in new ways, I enjoy looking at research at the primary grades, yes. Which was never really part of my research, but now I make a lot of connections to it. So I'm excited to be talking with you about that. First, though, since you're coming from over in Spain and different parts of the world, I want to just make sure I know a little bit about your background. So where did you do your doctoral studies, and who did you work with there?
I have just finished my doctoral study at the University of Alicante with the help of the Dr. Salvador Ginares and also the Dr. Mar Moreno, both from the University of Alicante as well, who have a long curricular research on mathematical didactics.
That's wonderful. And so you're having work from dissertation-related research already being published for the field, which is excellent. And you mentioned those two colleagues who are co-authors on the paper. So I want to move into this article. It involves a teaching experiment. So you had 59 students. They were about 9 or 10 years old. You did 10 sessions with these younger students. And it was the first time that they were really formally digging into polygons and learning about polygons in a formal way. So I wonder if you could just tell us, what was your approach to polygons? How did you approach that teaching experiment?
Yes, well, when students learn about polygon in school, they usually do tasks as what polygon class is shown in this figure. And these polygons are always presented with the same examples. These examples of polygon are what we call prototypical examples. If I ask you to think in an example of triangle, I'm sure that one of the first ones that comes to your mind is the equilateral triangle in a specific position. And it's normal because there are the example of polygon that we can see in the book, in dictionary, on television, everywhere. And this is a problem because these prototypical examples limit our ability to recognize part of polygon. That means the attributes of the polygons. On the other hand, research of geometric thinking has focused more on kindergarten and secondary school, but less has focused on primary school. So we wanted to investigate how a student in primary education, specifically in third grade, understand polygons and how they change the way of reasoning about the polygon after a certain instruction. We didn't want to base on textbook tasks. We designed a teaching experiment in which through 10 sessions, we wanted that students improve their ability to analyze geometric figures and endow mathematical meaning to the part of these figures in order to relate this meaning to the definition of geometric concept about to the polygon. This teaching experiment was sequential, and many of the concepts that we taught in the first session were used to support the concept in the last session. For example, in session 4, we dealt about the classes of angles, such as acute, right, or obtuse angles. And in the session 6, we deal with the classes of triangles according to their angles. Also, we show the student different samples and non-example of classes of polygon so that the student had a wide range of example of polygons.
Yeah, so this is great to hear about. I mean, I think there's really value in being thoughtful about the examples that are shared and trying to show a range and not just always going back to the same ones. And it sounds like you had a really nice plan for the sequence of those sessions. Just to help us dig into it a little bit more, can you share a couple examples of like specific activities and tasks that you did with the students?
Yes. One of the tasks we carried out with students to consolidate the geometric concept was, for example, to classify a sample of representative figures into classes of polygons. And then students have to explain why they belong to some class. For example, we showed to the student a set of polygons, and they had to classify the figures into concave or convex polygon. And then this student had to explain why one polygon belongs to a class or another. Another kind of task that we carry out so that the student could deal with the attribute of geometrical concept were tasks about building with didactic materials, such as the mechano is a material that are sticks of different color and lengths that are connected at the ends for building different polygons. In these tasks, the student has to take a level that showed a class of polygon, and then the student has to build it with this material, with the mechano. And we did this sort of task because we wanted that the student consolidate the attribute of the polygon classes.
Yeah, nice. So there's some comparison and sort of digging into specific details to classify, but then there's also building, and as you build it, you sort of feel how the different components go together, and you can discuss those too. Now, for the study, you have a questionnaire, and the questionnaire is one of the primary data sources for this study. I wonder if you could just tell us a little bit about what was on that questionnaire.
Yes, to test how the instruction that we carry out influenced to the reasoning of the student, we designed a questionnaire to be carried out after the instruction, whose tasks were addressed about 4 dimensions. These 4 dimensions are what for us is imply the understanding of polygon. This dimension address the ability to recognize polygon, that is the dimension 1. The dimension 2 is about being able to identify the common attribute of a set of polygon. The dimension 3 is about knowing how to determine if a polygon belongs or no to a class. And finally, the dimension 4 is related to drawing or building a polygon with given attributes. The questionnaire contains different tasks related to these 4 dimensions. For example, in relation to dimension 1, recognizing polygon, we design a task with a total of 5 items where a student has to recognize what figure were polygon and not polygon. And for example, other tasks were related to transform some non-polygon into polygon. And students have to explain the chain and then drawing the final polygon. For example, in one of these tasks, we showed an open figure with a curved side, and a student had to close the figure and change the curved side to a straight one. Another task that we show the dimension 2 related to identify the common attribute of a set of polygon is a task in which the student has to relate the attribute of the figure to identify the class that characterize each set of polygons. For this, we use the metaphor of the drawing machine, which can make certain polygons, what we understand as a sample of a class, and this machine cannot make other polygon, what we understand as non-sample of one class. So that the student could identify which class characterizes each set of polygons. Besides, the student has to explain what class about the set of polygon represented and had to draw an example and non-example of each class. One task representing a set of concave polygons, another set of polygon according to their sides, the number of sides, and other tasks about the symmetrical polygon and non-symmetrical polygons. Regarding to the dimension 3, about determining if a polygon belongs or not to a class, we created one task in which the student has to analyze an example of a representative figure and recognize if this figure belongs to a certain class or not, and justify the answer. For example, consider if a rhombus could be an example of symmetrical polygon. And about the dimension 4, related to drawing polygon with certain attributes, we design a task in which the student has to draw examples and non-examples of a certain polygon class. In particular, in this questionnaire, quadrilateral with at least 2 parallel sides.
So you worked with the students, these primary students throughout the 10 sessions, and you clearly kind of are focusing on these really creative and really in these ways that allow for deep exploration of polygons. And you're trying to build their conceptual understanding on these different dimensions, recognizing, being able to identify the attributes, being able to determine if it belongs to a class, and then also being able to construct something given some like we want it to have these characteristics, we want it to have this feature. Can you build such a thing? So I think we're now curious just to hear, what did you find? What were your main findings in terms of the students who've gone through this teaching experiment?
Well, for the analysis of the answer to the questionnaire, we carry out an implicative analysis with a program, a software called TIC. We use this software to see the quasi-logical implication that occur between the answer of the student to the questionnaire. From the way the graphs were formed, we can infer two relevant conclusions. The first of them was that the understanding of the polygon concept is progressive. First, one must know how to differentiate between examples and non-examples of polygon, and then the student be able to transform non-polygons into polygons. That is, we have been able to infer the result from the graph since it was shown in the upper part, which we can consider as a higher cognitive level, where the variable related to transforming non-polygon into polygon, where the student have to recognize which attributes do not belong to the definition of polygon in order to change them for that belong to the definition of polygon. And at the bottom of the graph were the variables related to recognize examples and non-example of polygon, where the student only have to relate the part of the figures to the definition of polygon to indicate if these figures are example or non-example of polygon, which they are more likely to answer correctly. This process of transforming is also progressive. The graph shows us that if a student can transform a non-example polygon that doesn't present any of the attributes of the polygon definition, then the student can transform non-example that present some attributes that don't belong to the polygon definition. That is, the student will be able to transform non-polygon into polygon by changing one attribute, then two attributes, and finally all the three attributes, being closed, straight sides, and non-closed sides. On the other hand, the second important finding is related to the classes of polygons. Being able to identify the common attribute of a set of polygons or to determine if a polygon belongs or not to a certain class. This action are linked to the process of recognizing parts in the figures and establishing relationship with the attribute that characterize the polygon classes. However, these two actions are cognitively different. By one hand, recognizing allows us to see the necessary part of a figure to endow them mathematical meaning, and therefore determine if that figure belongs to one class or another. But the action of identifying involves seeing the part of a figure, endowing them mathematical meaning, relating this part to the part of another figure, which is perceptually different from the first, in order to determine if these figures belong to the same polygon class. For this reason, the variables related to the recognize are at the bottom of the graph, and the variables related to identify the common attribute in a set of polygons, which are more complex, are at the top of the graph. Additionally, graph has shown us that the understanding of polygon classes depends on the attribute. That is, the quasi-implicative graphs show the relevance of symmetry and parallel sides in the understanding of polygon classes. For this reason, these variables are at the top of the graph. So if a student recognizes these attributes, then they may be able to recognize other attributes, such as number of sides, clustering of triangles, or concavity or convexity. But these graphs cannot be interpreted in reverse. So if a student identifies concavity or number of sides, this student couldn't identify or will be able to identify the symmetry.
Yeah, like they not necessarily would identify the symmetry, going that direction. So having thought about like designing the teaching experiment and now looking in detail at the findings that you were describing, what are the implications that you are drawing from this analysis?
From the analysis of the student response to the questionnaire after instruction, we can highlight that the teaching of geometry shows students more examples and non-examples of polygon classes so that they can recognize attributes, transforming non-example of a polygon class into a sample of another class, explaining and drawing this transformation so that the student can build a solid understanding of the concept of polygon and polygon classes. Also, in schools, the analysis of geometric figures should also be encouraged to support the ability of a student to differentiate figures, taking into account various attributes and the ability to endow mathematical meaning to the parts of the figures. Another idea will be that the teacher should provide the student with tasks to allow them to recognize figures as a sample of classes of polygon, always justifying their membership.
Yeah, and I think those ones where you're trying to see, does this belong in a class, and we have to justify it, those are the most fun when you have outliers. Like you have weird examples that don't seem like on first impression that they should be part of the class, but that's one where it can be fun to justify it. Like, no, I can make a case that it meets all of the definition, like all of the criteria to be in the class, so you have to let it in the class, rather than, like you said at the start, rather than always showing like the most prototypical obvious examples. There's not much debate that's going to happen around those. And I think too, I just really resonate with your focus on examples and non-examples as a way to talk and dig into ideas. With my colleague Xandra Diaraggio and I, we've been having a lot of fun in secondary levels, in algebra and in a lot of topics, having fun with examples and non-examples because it can really generate a lot of good conversation.
Yeah.
My guest is Melania Bernabeu from Universidad de Alicante, and I've really appreciated hearing about your work with the primary grades and polygons. I do have a final question that I like to end with. And I know you're right at the start of your academic career, having finished your doctoral studies and moving forward in a good way. But maybe just imagine if you were not in mathematics education. Is there something you could think of that might have been an alternative career for you?
Well, the truth is that I have always liked mathematics since I was young. But if I have to choose another profession, I don't know, but maybe I would have liked to be a teacher of technical drawing. I love using the ruler, the compass, the ink pens to build geometric objects in 3 dimensions and to see the final result. The truth is that I really enjoy this subject at high school, but I knew that to become a teacher of this subject, I had to study fine arts, and also I like painting. I'm not very good at this skill. Possible I will still continue studying this degree. It's all related, technical drawing and mathematics, so I guess I will have worked in a profession related to geometry in the end.
Well, it's been good talking to you. Thanks so much for being on the podcast.
Thank you, and gracias.